Hello everyone! In this control engineering and process control tutorial, we explain how to model and implement a PID controller for controlling a fluid level inside of a tank or reservoir, and we explain how to simulate the PID controller and the complete closed-loop system in Simulink and MATLAB. The problem that we are addressing in this video tutorial is one of the most important and fundamental problems in chemical engineering, mechanical engineering, and process engineering. The sketch of the water tank is given over here. The goal is to control the liquid level, denoted by H, by controlling the input flow rate Q input. This equation over here represents the dynamical model of the system, and this equation is derived in our previous tutorial, whose link is given in the description below. The dynamics of this system is nonlinear due to this square root function. Furthermore, the closed-loop system will contain additional nonlinearities coming from the actuator saturation and limits. In this tutorial, we explain how to model this nonlinear dynamics of the fluid tank and how to implement and test a PID controller for such a nonlinear system in Simulink. This block diagram represents the Simulink model of the complete closed-loop system. By the end of this tutorial, you will learn how to create and simulate this closed-loop system in Simulink and MATLAB. A link to the Simulink file containing this block diagram and this model is also given in the description below this video. For example, this block over here represents the nonlinear dynamics of our tank system. Here it is. Then, here's our PID controller, proportional term, integral term, and derivative term over here. Here, we can change the set point. That is, we can change the desired value of the water level. For example, we can specify 1 over here. That is, we want our closed-loop system to maintain 1 meter of water level in our tank. Let's run this simulation. Then, if you double-click over here, you will see two curves. This blue curve represents the controlled water level, and the yellow curve represents the control input, that is, the input flow rate. You can play with the set point. For example, let's change over here the set point to 2. Okay, and then run the simulation once more, and let's see the results. Here they are. We can see that the water level goes to 2 after some transient response. Okay, let's start. First, we will briefly describe the system and briefly state the problem formulation. We consider a tank with a cross-section area of A filled with an incompressible fluid such as water, for example. The fluid level at the time instant t is H. The input volumetric flow rate to the tank is denoted by QIN, where this IN stands for the input. The output volumetric flow rate coming out of the tank is Q out. We assume that the output flow rate is passive. That is, we assume that we cannot control Q out. Then we assume that the cross-section area of the hole is much smaller than the cross-section area A of the tank. Also, we assume that we can directly control the input flow rate QIN. Under these assumptions, in our previous tutorial, whose link is given in the description below, we derive a differential equation describing the dynamics of the fluid level H, and the equation is given over here. In this equation, A is the cross-section area of the tank and C is a constant. Here is the complete block diagram of the closed-loop system. This block over here represents the dynamics of our tank. The dynamics is described by this differential equation. Let's identify the inputs and outputs of this block. The input is QIN. QIN is the input flow rate to the tank, and here's the term over here. The output is H. That is, over here we assume that there is a sensor measuring the fluid level inside of the tank. The dynamics of H is described by this nonlinear differential equation. This block over here is our PID controller. For those of you who don't know what is a PID, PID stands for Proportional Integral Derivative Controller. The input to our PID controller is the error. Now, what is the error? The error is the difference between H desired and true H. H desired is the desired fluid level in the tank. This is our set point. And H is the true or the measured value of the fluid level. The output of the PID controller is the control input. Here is the equation representing the mathematical model of our PID controller. Kp, Kd, and Ki are the constants. These are proportional constant, derivative action constant, and the integral action constant. Over here, S is the complex Laplace variable, and E is the error. The output of the PID controller is U. U is the input to this saturation and limit block. What is the purpose of this block? The purpose of this block is to model the physical limitations of our pump. Namely, you cannot produce a flow that has infinite flow rate. That's why we have the saturation over here. For example, you can only produce the flow up to 5 cubic meters per second. Then, another limitation is that we cannot produce negative flows. That is, the pump can usually only spin in one direction and it cannot actually spin in the other direction. That is, the pump can only pump water to the tank and cannot pump the water out of the tank. This is very important. This block over here is very important for control algorithms. Again, the input to this block is U, that is the output of our PID controller, and the output of this block is QIN, that is the flow rate. This flow rate goes inside of the tank dynamics, then it goes through this dynamics, then again we have the measurement, then we have a feedback over here, we calculate the error, and this is how our PID and closed loop systems work. In the sequel, we will develop the MATLAB and the Simulink models. The first step is to define the model parameters. The model parameters are A, that is the cross-section area of our tank, and this constant C over here. Over here, I will assume that the radius of my tank is equal to 1 meter. That is, I'm assuming that the tank is circular with a radius of 1 meter. Consequently, the cross-section area is given over here. The constant C is derived in our previous tutorial, and here is the expression. I'm assuming a discharge coefficient of 0.6, and this is a constant. Actually, this is square root of 2g. Then, I need to define the parameters of my proportional, derivative, and integral controller. And here they are. Here is the proportional gain, here is the derivative gain, and here is the integral gain. You can play with these parameters later on, and you can test the performance of the closed loop system for different values of these parameters. First, evaluate this script. It's very important that these parameters are in the MATLAB workspace before you start with Simulink modeling. Next, let's open the Simulink by typing Simulink. Let's click on the blank model, and our first step is to model the dynamics of our system. That is, we need to model the nonlinear differential equation representing the change of the fluid level inside of the tank. Here, for the presentation clarity, let's write our dynamics once more. Our dynamics looks like this. dH over dt is equal to 1 over a multiplying q input minus c over a multiplying square root of h. Here q input is the input and h is the fluid level inside of the tank. From this equation it follows that h is actually an integral of everything that's on the right hand side. That is an integral of 1 over a multiplying q input minus c over a multiplying square root of h dt. Good. From this equation we can see that the first step in modeling of this differential equation is actually to model the integral term. To add the integral term, double-click over here and search for integrator. Here it is. Enlarge this block. The output of the integrator is actually RH. The next step is to model this nonlinearity. This is a root, or better to say a square root nonlinearity, and to model it, double-click over here and search for root, and you will find square root. Next, click on Format and click over here to rotate this block. Connect the output of the integrator to the input of the square root, and you will obtain square root of h. Next, we need to multiply square root of h with c over a. To do that, we need to add the gain. Double-click over here and search for a gain. Again, rotate the gain, click on Format and click over here to rotate the gain. Enlarge the gain block. Align the lines, connect them, double-click over here, and over here type c over a. Note over here that Simulink is smart enough to recognize that a is inside of the MATLAB memory. This is because we have previously evaluated the script that defines these constants. Perfect. Now we have c over a multiplying square root of h. Next, we need to add a summation block. Double-click over here and search for sum. Enlarge the sum, double-click on the sum, and change this last plus to the minus. Click OK and connect the output of this gain to this minus port. Good, now we have minus c over a multiplying square root of h. Perfect. Next we need to add q input. Note over here that q input will be the output of the saturation limit. However, in order to test our dynamics, we will simply model the q input as a constant. Double-click over here and search for a constant. Here you can change the value of this constant. Double-click here and let's say, for example, specify 2. This means that we are setting qin to be equal to 2. That is, we are setting the input flow rate to 2. Next, we need to add this constant over here, multiplying qin. Double-click here and search for gain. Expand the gain, connect the proper ports, double-click on the gain, and type over here 1 over a. Here it is. Click OK, connect these blocks, this block and this block, double-click over here and search for scope, and connect the output to the scope. Perfect. Double check that everything is okay. Square root of h, c over a, minus qin multiplying 1 over a. We add these two terms over here. We integrate everything to obtain h, and we will plot the results. Let's simulate these dynamics by clicking over here. Change the stop time, for example, to 40, and click on Run to run the simulation. Double-click over here to see the results, and here it is. We can see the output H, that is the fluid tank level. We can see how it nicely increases once we turn on the pump, and the pump delivers constant flow rate. When modeling complex systems in Simulink, it's always a good practice to split your complex model into simpler subblocks. So let's do it over here. Select everything over here, then click on these 3 dots and click on Create Subsystem. And here it is. Instead of our nonlinear dynamics, we will see a simple subsystem. Double-click on this subsystem and you will see your nonlinear dynamics. You can go back by clicking over here. Good. Next, erase this part over here and erase this part. But before you do that, let's run the simulation once more to make sure that we didn't miss any part over here. Expand the scope. Good. And that's it. Okay, now we can erase this block. We can erase this arrow, we can erase this arrow, and we can erase this block. Perfect. Next, we need to model the PID controller and the saturation limit block. Let's write the main equation of the PID controller in the S domain. The input U generated by the PID controller is equal to proportional gain multiplying the error plus the derivative gain multiplying the S, and S is the Laplace complex variable, multiplying the error, plus integral gain, Ki, over S multiplying the error. The error is defined as H desired, that is the desired level minus the measured level. Let's model this PID controller. Obviously, first we need to create the error. To create the error, double-click over here and search for sum. Enlarge the sum block and let's move this part over here. Double-click on sum and change this last plus to the minus. Good. Let's continue. The output of our nonlinear dynamics is actually H. And over here, we assume that there is an ideal sensor measuring the tank level. That is the liquid level inside of the tank. Since the sensor is completely ideal, we don't model the sensor. That is, the sensor is simple constant equal to 1. Good. On this side, we need to have H desired. We will model H desired as a simple constant. That is, the desired value of the fluid level inside of the tank will be a constant. Double-click over here and search for constant. And here it is. For the time being, let's keep this constant to 1. Connect this part over here and good. Now, the output of this minus and plus block is actually the error. Next, we need to model our PID controller. Move this part a little bit here, such that we have more space. And let's model the proportional part of our PID. We need to get Kp. Double-click over here and search for a gain. Here's the gain. Double-click on the gain, and over here type Kp. Notice over here that Kp is already in the MATLAB workspace. Good. Next, you need to connect this part to Kp, and let's model our derivative action. To model the derivative action, again, we need to double-click, type gain, double-click over here once more, and type Kd, and click OK. Connect over here. Next, we need a derivative action. Double-click over here and search for derivative. Connect the proper blocks. And here's our derivative action. Here, I need to make one important comment. Usually in practice, we will not model the derivative action like this. This is because the pure derivative action will amplify the high frequency components of our error, and we don't want to do that. Instead, a better idea is to model our derivative action like this. Kd multiplying S over some constant t multiplying S plus 1. What will happen over here? Until 1 over t, basically, where t is a user-selected parameter, this term over here, or better to say, this transfer function will act as a derivative action. After 1 over t frequency, we will see that the transfer function, or better to say its Bode plot, will decay. And this will actually limit, or better to say, make sure that the high frequency components are not exaggerated and they're not amplified. That is, in practice, we will combine a derivative action with a low pass filter to limit the amplification of high frequency components of the error. However, for the time being, we will simply model the derivative action as a simple derivative term, that is, as a simple differentiator. Okay, let me erase this so I can continue. Next, we need to model our integral term over here. Double click here and again search for gain. Double click on gain and type Ki over here. Click on OK. Connect these parts. Double click over here and search for an integrator. Here's our integrator. Connect the blocks. And now we need to sum our proportional, derivative, and integral actions. We can do that by clicking over here and searching for the add block. Here it is. Double click on the add block and add an extra plus over here. And next you can simply connect the blocks to the add term. Good. Now we have Kp multiplying E, this part here, Kd multiplying S multiplying E, this part over here, and Ki multiplying 1 over S multiplying E, that is this part over here. The next step is to model the saturation block. Here is our saturation block. The saturation block will put to 0 all the control inputs smaller than 0. This means that we don't allow our pump to move in the opposite direction. Furthermore, the values of U that are larger than some critical value will be set to Q input max. That is, we will limit the flow rate. Let's do that. To model this block, double-click here and search for limit. Or better to say, search for saturation. This is the correct block. Search for saturation and not limit. Double-click on the saturation and set the lower limit to 0, and let's set the upper limit to 5, for example. This will limit the input flow rate to 5 cubic meters per second. Next, connect the parts together, and that's it. The next step is to add the MUX block. The MUX block will enable us to plot on the same scope two signals. First of all, we will plot this input signal and we will plot the water level H. Double click over here and search for MUX. Next, connect the blocks. This block should be connected over here, or better say, this line should be connected to the first input port, and the second input port should be connected to the output. Good. Double click here and search for scope. Here is the scope, and connect the scope to the MUX block. Now we are ready to simulate our closed loop system. To simulate the closed loop system, make sure that stop time is 40 and click on run. Okay, let's see the output. Double click on the scope. And we can see a very nice result. We can see there that this blue line representing our water level goes to 1. And 1 is our desired water level. And we can see over here this yellow line representing the input flow rate increases steadily. Perfect. Next, let's try to make this response of our system to be faster by increasing the control gains. First of all, to get a faster response, we can increase the proportional gain. For example, let's set the proportional gain to be equal to 2. And we can also increase the integral gain, for example 0.4. Let's evaluate this script such that all the parameters are inside of our MATLAB workspace, and let's go back to Simulink and let's simulate the model once more. Let's run the simulation once more. And let's observe the output. We can see that the output is faster right now. And you can play with the control parameters and you can try to tune this control algorithm. Next, Let's illustrate the effect of this saturation block. Let us increase the desired set value. For example, let's say that we want our water level to be equal to 4 meters. However, here we will have the input flow rate to 5. That's the maximum value that our pump can produce. Click on OK and let's run the simulation. Let's look at the output. What's happening over here? Well, our desired water level is 4. However, we can see that our control algorithm cannot achieve this desired water level. Why is that? Well, we can see that we reach the maximum value, or better to say, the maximum physical value that our pump can produce. Our pump cannot produce more than 5 cubic meters per second. And that's why we cannot reach the desired set point. Let's say that we invested more money in our experimental setup and that we change the pump. Over here, I will increase the upper limit for the pump since we purchased more expensive pump that can pump more waters per second, or better to say, more fluid or more cubic meters per second, and click on OK. Let's now run the simulation once more, and let's look at the output. And you can see that we can actually reach the desired value. And this is the direct effect of our saturation limits. Okay, that's all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.